Welcome to lecture 18. Um, we had a discussion on data subset selection in the last class, but let's conclude our discussion on the whole notion of subgradient descent um, through stochastic gradient descent. We brought in stochasticity where we didn't want to incur the computational cost of computing the subgradient on the entire data set. So as a homework, I had kind of left for you to mull over um, some aspects that stochastic gradient descent brought us. So recall that while classical gradient descent, we were able to make use of something like Lipschitz continuity. In stochastic gradient descent, we're looking at kind of Lipschitz continuity and expectation. Okay, and there we had this Jensen's inequality, um, and by this Jensen's inequality, the ordinary Lipschitz continuity constant is kind of a lower bound on or is upper bounded by the stochastic gradient descent Lipschitz constant. Yeah, and we will talk about mini batch very soon today. Um, but if you use the notion of mini batches, then this gap can be um, bridged somewhat. So this gap, okay. Um, and I left you with this homework, was where you could look at the full versus stochastic. You find that under normal convexity assumptions, they are very comparable, right? And if you do that's with subgradient analysis, and if you do strong convexity, again they're comparable. However, if you do strong convexity with gradient descent, then there is a gap, and it's a big gap, right? This is called linear convergence on the left hand side. We saw for tenfold increase, you just need a constant number of step size. So this is the probably the only gap that we will try and bridge now. Again, the convergence analysis to just show that there's something amiss, something more can be done. Okay, so what else do you get from this slide? Anything else? This is a homework problem, right? I give you one possible improvement. What else do you get from this slide? Just because all of these are comparable, have you got nothing out of stochastic? Might as well go back to the non-stochastic version. How did the number come? Oh, comparable in the sense that no, no, oh, sorry. These are not. Yeah, this is also. Yeah, I meant these. Right? These were comparable. This is not. This still is, I would say, not significant gap, right? Yeah, this is also correct. So, less significant gap. There is a gap, whereas these were comparable. Okay, so certainly we want to bridge these two gaps. What else do you get from this slide? we should have mentioned something more, right? Uh, is there nothing that stochastic gradient descent is giving you, even in the subgradient case? So what should have been noted additionally? In the stochastic case, yes, 4 iterations. Um, doesn't look like in the subgradient case. Yeah, there is a gap in the gradient case. Okay, so there's more. The gradient gap calculation is going to be much cheaper in the stochastic case, right? So that is the advantage you're getting in the first place, right? So how much is the gain? So if you have n examples, each epoch is n times faster, right? Well, I mean, I want so epoch, each iteration, not epoch, right? Epoch typically is when you have iterated over the entire data set. So each iteration of update n times faster. And what is that? Because faster than the case of full iteration as in gradient descent. Okay, so that's something we have gained in the stochastic case. Yeah. But what we have also pointed out is that for smooth problems there seems to be a big gap, and that's the part here on the. So this part is still a bother for us for smooth problems. This gap, we are still concerned about it. Okay, so let's try and see how we can fix that. Um, there's one more point I want to drive before we proceed. I mean, there's one more kind of homework based observation. Um, we already pointed out that the stochastic gradient descent will have an unbiased estimate of the gradient, right? So what did we note? That the expectation of the gradient. So I'll be using some notation in the next slide, but in anticipation, I can just say that. So let's just call this, tilde, g tilde t given wt, current set of parameters, is the same as the expected value of the gradient as per the full update. Okay. That's a gt tilde. Oh, I'm sorry. Yeah, obviously. Okay. Whereas what we have on the left hand side is the expectation. So this is based on uh, sampling uniformly at random. Okay, that's an assumption. Okay, so now what do you think? The left side is sampling with replacement. Correct. So that's another issue I pointed out, that in practice, what would you do? You would actually, would you replace in practice?
I mean, at least in theory, you should have to need to do replacement, because if you do it without replacement, the analysis will become very complicated because of all the different variables.
Right, right. So there is a slight discrepancy between theory and practice here. Okay, but there is another bigger issue here. So that certainly is a discrepancy to be resolved with and without replacement. But what about the variance? What do you think will happen to the variance? So what do you think is the variance? Let's say variance of the norm square. So we are dealing with a vector. So some kind of metric associated with gt tilde. So I'll leave it at this, right? So want to put a norm, that's also fine. What about this? Okay, so what I wrote earlier, I'll try and bring it back. So whether you call it GT or whether you call it expectation, it's the same. Basically, it's okay to write about GT um, as an expectation, right? So the expectations were matching, but what happens to the variance? I can't write an exact expression here, but
Can you repeat the expression that T is V square?
right, but qualitatively, you expect it to be high. So what we are trying to I'll point out is that the solution we are seeking for the smooth problem case is very related to reducing the variance, okay, in some sense. I mean, there will be more things else as well. So something ms, right, and reducing the variance will probably have related approaches. Okay. So with that note, let's move on. And that turns out that one small fix and maybe several follow-ups to this, which might help us out, is a notion of mini batch stochastic gradient. So instead of taking single instances, you're basically taking a batch and then taking an average. Okay, so this is the now g tilde t is not just a single example, but a batch of them, average of the batch, and of which you have simple extreme cases. Okay, the extreme case where you are dealing with, say, it's a single, which is stochastic gradient descent, or what we saw on the previous slide, m equals n is a full gradient descent. Okay, so believing that the variance was very high earlier, now the variance is going to be reduced. So maybe I should just go back to the previous slide and not call it tilde alone. Maybe I'll just put it as a so this is stochastic. So I'll just put it as superscript s. Okay, so superscript s. So this is g tilde. This is batch based. So what the statement says that the gradient estimate has now reduced to 1 upon m of that of vanilla SGD. So um, so basically what you're saying is the expectation will remain the same, but whereas the variance with this new g tilde t given wt is 1 upon m times the variance of the single instance based stochastic WT, GT tilde WS. It might be a good idea for me to just put some norm here. Basically, I'm trying to measure. Okay. So the whole thing is in terms of norm. It's a magnitude. Okay. Yeah, I should put a norm here as well. So that's very important because stability is very vital to the performance of SGD. Okay, so you can also do subgradient. I think that goes without saying. Subgradient can always replace gradient implementation wise. But again, what is the implication of this for mini batch? So earlier we were just sampling I in n uniformly at random. So iteration you have n times cheaper than the full subgradient descent. This is again for stochastic. Um, where we use an unbiased estimate of the subgradient at each step. So this give you convergence in omega 1 by epsilon square. Now if I imagine I were to add mini batch, okay, so what would mini batch do? How would it modify the algorithm? Yes, what are the places I'll modify the algorithm? Here. So um, so what are the pros and cons? Reduction and variance. So that I've already mentioned as a pro. But what is negative?
You won't enjoy the n times cheaper.
You won't have the n times cheaper, right? So this n times cheaper with stochastic will become, sorry, with mini batch will become what? So let's say sampling a batch of size B. Okay, so fixed size B. Then how would things change?
N by 2.
Yeah, stochastic mini batch n by B times cheaper. Right? While having maybe reasonably controlled variance, and it's natural, right? So if the variance, if you take the extreme case where the m equals n, right? Then you'd basically have you'll recover the invariance also, right? 1 upon n. Okay. So very quickly, like in text, let's just understand why machine learning um, people prefer batched variants um, of stochastic gradient descent. Well, so stochastic gradient descent is slow compared to gradient descent in convergence. That's a practical aspect. Um, so though gradient is unbiased, it is noisy. That's what we meant by high variance. And there's not guarantee that you'll have reduced objective at each iteration. Therefore, I said both the subgradient and stochastic, calling them descent itself is a misnomer. a descent okay, and the learning rate setting has now really gone for a toss. The RMEO condition, the strong wolf conditions, and we talked about RMEO different versions, and there was a motivation, there was some quadratic interpolation, um, there was also kind of exponential decay that we were trying to counter. All that goes out of the window. So most of it, rather, it becomes more of a art than a science. So those are the cons. What are the pros? Besides speed up, anyone on the call as well? So one is certainly speed up, but then what else? Machine learning. So we are discussing not just optimization. We have moved to machine learning. Right. So actually, I have brought that picture later on, but let me copy this here as well. Okay, yeah, yeah. Um, I'll discuss this from different perspective. The pro one pro could be that you are you have the capacity to escape local minima. Okay, so the left hand case is not an issue. But let's discuss the right hand case, right? So the convex case, it's not going to help much, right? Let's say there's a local minimum here. So whereas gradient descent might try and get to this local minimum, there's a local minimum here. Stochastic gradient descent might help you jump just because your stochastic view is not the same as the entire data view. That's it. That's basically it. So it might lead to escaping local minima and therefore generalization. Might generalize well. Local minimum is also aspect of overfitting. But even if you consider the escaping of you know global minimum, sometimes that's also possible. If got a convex problem, it can even escape local global minimum. Even then, a stronger point in its favor, I would say, is might help generalize. That's just because it's stochastic. You're taking a point completely at random. So, and that random point might be an adversarial point, a point difficult to classify. Of course, you're not really pick the point which is difficult to classify. You can get fancier there, but might help generalize. That's our intuition as of now. Better, um, especially when the point randomly picked are adversarial. Okay, so it might be that the point is adversarial in the sense that it's helped you escape the local minimum. Maybe because it's just very difficult to classify. Oh, so it could be sitting out somewhere. Okay, but there are a couple of other advantages. This is one pro, but let's the other more routine ones are per iteration cost is n times cheaper, or in the case of n by b, in the case of batch, it's n by b. Initial convergence is very fast. Why would you think this happens? And I would say this is not necessarily for deep ML. So some you may say it's very non-convex, therefore But let me put a disclaimer here. Okay, let me type it. So why do you think this happens? Any explanations? You remember we talked about, we motivated in the last class about using subset selection, finding the right subset. What was all that for?
As you can say that if the data is homogeneous statistically, then even a mini batch is a representative of the entire data set. So what we actually need is a small representation of the entire data set.
So you need a the answer is you need, or one answer suggested is you need a representation of the entire data set, a summary of the entire data set, because the data set has some amount of redundancy, right? Okay, so you need to represent, right? I mean, either be batch to represent effectively, right? So so of course we have not been most effective in just taking a point randomly. But if the data set is super redundant, extremely homogeneous, then any random point will be as good. And therefore, that brings us to the next point, that if you, I mean, so because the data set is not so super homogeneous, therefore, in practice, the representation through a mini batch works well. So mini batch is a more practical more practical approach for representation. Okay, yeah. Let me know if you want me to stop at any point of time. Um, okay, so basically, the other aspect is that we are more interested in getting generalization than just get a global minima, right? So again, I bring back this. So you may be attaining a local minima, but or even a global minima. So even if you're attaining this point, what you want to generalize do is generalize well. Um, and from machine learning, we know that if what you see well on the trading set may not generalize to the test set. So stochastic gradient descent, for the reasons I've been talking about, generalizes generally much better. Um, but however, there's a big gap between the theory of stochastic gradient descent, and we'll see, some analysis to regret bound. More of it as extra reading, otherwise we'll be stuck on this for too long. Um, so there's still a large gap, and if a lot of this black magic is because of the learning rate, right? At least we had some motivation for learning rate, existential in terms of Lipschitz smooth function. There we're talking about minimizing an upper bound. Many of those things don't work out well here. Okay, so very complex learning rate rules are there. So the analysis, when we say theory, we're talking about two things. One is I know that the fact that analysis is largely through expected values. The other thing we'll brief very extra optional reading, which I'll probably just run through, is regret bound. It's an online learning where you have access to seeing one point or a bunch of points at a time, processing them for updating your parameters. Okay. Um, yeah, just further emphasizing on that point of step sizes or learning rates. So the learning rates are the most non-trivial part. As you can see, these two pictures, um, for convex and non-convex, it's so unclear what it's going to be. Right? Learning rate part. So when the learning rate is too large, the gradient descent can inadvertently, inadvertently increase rather than decrease the training error. And so that in the convex case we see in the picture above. That's the reason I put this image. So here you see that the learning rate is too large. But at the same time, it could also help you get out of a local minimum. That's also possible. So it's relative. So if it's too small, training is not only slower, but it may just get stuck with a local minimum, high training error, and I would say more generally also local minimum. Right? And somebody may say, okay, um, why not just treat it as a hyperparameter, the learning rate itself? The learning rate can be then the hyperparameter, that's worth tuning. But if that's only possible if there's only one hyperparameter, I mean, if there are too many hyperparameters, you have model architecture, you have, regularization constant, then again you're asking for too much. Okay, and if using a fixed learning rate, uh, you should tune it over a validation set. It's just one fixed. But if there's a learning rate schedule, then you have a bigger problem. Okay, so then there are also learning rate schedules. For example, linear rate decay, cyclic, cyclic. So you kind of increase and then decrease. So there are a whole bunch of, I'll just say linear and cyclic rates. Many of those are implemented in uh, PyTorch. I mean, provided as options. Right. But if you have learning rate decay, then stochastic gradient descent somehow becomes more robust to the initial learning rate where you begin. Okay, so this is just more of a general discussion. Um, but I'm going to give you some more generic principles now to before we look at the next set. So we want to improve the convergence rate of SGD, and we saw especially strong convexity, right? So let's write down things that bother us and see how we can improve on those. Okay, points that bother us. You can help me, right? Obviously, you can say subset selection. We'll come to that maybe in one or two classes. But what are other points that immediately bother us? We try and reduce the variance, but is that only is that resolved for once and for all? Why did the use of a batch actually reduce variance? Can that principle be reused? Okay, so can I say, um, how can we derive principle a principle for reducing variance? Let's say I come up with accelerated versions. So acceleration also I want to reduce the variance. What's that basic idea? Is mini batch the only way of reducing variance? And why does mini batch reduce variance in the first place? Okay, so we'll try and look at this. Um, I have mentioned a point here. HDD has much lower complexity per iteration, but it can have much slower convergence. So can we increase the convergence, improve the convergence of HDD? What comes to your mind?
learning rate learning scheduling.
Okay, learning. Okay, okay, learning rate, schedules. What else? Acceleration. Anything else that comes to your mind? Actually, acceleration means momentum. Any other point from those on the call?
We can do subset selection and filter for
So
that.
subset selection, yeah. So subset selection. I won't go into that right now. We'll directly jump to solutions a little later. Anything else? Yeah, there's one point we want to specifically hammer, right? The gap we found between strong convexity, that was a bit too much. A linear rate to this 1 upon t is like too much, too embarrassing. Okay. The case of strong convexity, can the gap be reduced? So I must point out that the reduction in gap in the case of strong convexity is very related to reducing variance also. Actually, the two are related, so I'm going to highlight them in the same color. So this point, um, reducing variance, principle for reducing variance is something we'll actually reuse for both. Reducing the gap in the case of strong convexity, or even just convexity, but strong convexity was certainly a bother for us. Okay. Um, Anything else that comes to mind, or should we move on? Right. So we have the same low cost per iteration, but with the convergence of gradient descent and so on. So we are getting a little ambitious here. Okay. So I'm going to start with the first basic principle for reducing variance. What happened when I consider a mini batch? And a mini batch in the asymptotic extreme case could be the entire set itself, right? The entire set. Um, so entire set means that the randomness has reduced. I mean, there's no random choice. Mini batch has kind of reduced the randomness. You see, the way you reduce randomness is by adding a. So if I want to reduce the randomness associated with generating a number, can I add a constant to reduce that number randomness? Right. So we'll see that this is related to kind of bringing in some constant, some constant factor. I won't say constant, but constant factor. Additive, additive. Very good point. Some additive constant factor. Okay. So can I suggest that that constant factor could come from, so let's say every time I sample an example, I find its gradient. Should I just throw away that gradient? Over a course of time, let's say I've actually landed up scanning every point. For every point, I have access to its gradient in some previous epoch. May not be the most recent one. Can I treat those as kind of constants, additive constants? Okay. So let me just write that down. Okay. So my question is, instead of computing and then computing gradients on randomly chosen points and then discarding them, can such computations be accumulated and made to contribute to some form of additive constant? I mean, it's constant I'm using within quotes. It's not really constant. It's going to change, but it's basically pulling back things. I mean, I don't expect the gradient at the same point to change too much across iterations, right? So if whether I use the gradient of the point from the previous iteration or 10 iterations back, probably may not make a big difference. Okay, so that is the basic idea behind our next approach, the hybrid kind of approach, SGD, or stochastic average gradient, 2012. That's the first kind of jump in this space. So store the gradients for I equals 1 to n, right? And then select uniformly at random some IT uh, only for this uniformly random choice IT. What do you do? So if I equals IT, you basically sum across all of them, but only if I equals IT, you compute the new gradient. For all the others, you have the stored gradients. So for all the others, you call it, GT, this unit name. This is the GT minus 1I that we see later on. Okay, it's like a cache. But that cache might be out of sync with reality, but that's okay. Okay, so you may want to expand this. So you may say that this is nothing but Wt plus 1 equals Wt minus gamma t divided by n, the gradient of it, or gradient of f at it, point it, minus some constant. Okay, minus plus, or I mean call it plus constant, which is a negative value. Okay, so this is what we were referring to as an additive constant. The previous slide, right? This additive constant factor. Because this will not change much across epochs. Okay, so now you look at it. All that you have now to do is some storage, and even that additional stored constant, you'll have to just incrementally update it for the points that have changed. Subtract and add maybe, right? Because this new point is going to change the constant for the next epoch, but very marginally. There's a little bit of storage issue, but I mean, depends on do you need to store the, because now when you have this constant, you'll have to subtract, right? You need to know the gradients of all the points, gradients of the function at the points in the previous epoch. That will require a lot of a lot of storage. Computational wise, overhead is less. So yeah.
in case of stochastic gradient, you well said that the computation for iteration is one by n because we are computing the gradient for only one point. But in this case, we are computing the gradient for in all the points in every iteration.
Not all the points in every iteration. They are from the previous iterations.
Then G is the gradient of uh, the point at the previous iteration or the update we receive during the gradient.
No, no, no. The gradient in some previous iteration. Nothing was updated. Yeah, otherwise the whole point is defeated. Then you're back to full. If you start, the question, sorry, was is GT minus one I, right? This like a cache. Is this going to be updated at every epoch? No, the point is defeated, right? Like a cache with stale entries. For large data set, very few times. Ah, um, that's a good point. So there are some engineering tricks also that get employed. Now, the question was, if you are not going to, use all of these, compute all of these points very regularly, just very old values, then that staleness wouldn't it hurt more than help? That's the question, right? So there are multiple tricks around this, and you'll see, there are lots of follow-up works. This is, as I said, this is the first initial idea. The staleness can hurt. So you could take a mini batch at every epoch. You could take, once in a while you can flush your entire cache. You can compute all the gradients from scratch. So all kinds of variants exist, right? But the uh, basic idea is to build around this. Okay. So yeah, the storage overhead is what I had talked about. There's that additional um, constant, right? So that incurs storage overhead, and that's acceptable in some ML settings. So you'll have to basically now compute this and store it. Right? But now what you may do is, okay, this phi AI, right? You instead of since the whole thing is like depending on X transpose phi AI, let's say, let's say in the case of logistic regression classify, you're looking at this dot product and a sigmoid around that. Right? So what should you store? I mean, you have to store a little intelligently. The points are not changing. The parameters are changing. Right? So the AIs are not changing. X is changing. Sorry, X is basically not the point. It's the parameter. So just note this. A is a point. Y is a label of that point. So phi's are not changing. So is there a way we can now do this X transpose phi more efficiently? Okay, so yeah, you'll have to just store the n scalars corresponding to the components in X, but compute this more efficiently. So these are engineering tricks. Okay. Um, what I'll do is I'll just quickly show you. Okay, this one. So there's a bunch of slides. Um, why did it not? So it's a bunch of slides from Pradeep Ravi Kumar on the different variants of stochastic average gradient. That's what we saw, right? SAG, which I said was a breakthrough method. Um, but then that has been improvised upon. These are not my slides, so I'm just showing those slides as they are. So some of the questions you are asking, right? Isn't it expensive to average all these gradients? Right? But you have to be a little clever. So you have to keep a table of old, right, average, update that, but you'll still have to store some parameters to be able to update. So there have been variants. Some of you had a problem, right? Is the Are we carrying too much old baggage, right? So this approach tries to address. Okay, so tries to address the issue of carrying a very stale cache. So it's called SAG variance. I mean, basically you can see how variance reduction could be achieved. Oh, this is variance reduction. I think I'll talk to SVRG. Sorry, this one. Yeah, so these are other versions. Saga. Um, but let me go to SVRG. Yeah, okay, this one SVRG, which came much later. This is what I was referring to. So it says, okay, I'm going to keep that overall average mu tilde. So the notations change. That I'll not spend too much time. The notations here, W is not the parameter, X is the parameter, right? So, but what you're also trying to do is for a mini batch, you're trying to compute the latest update as well. Okay, so not for the entire. So um, I mean, if you're going to do this every iteration for all the points, you're back to old days, which we want to avoid. Okay, so yeah, I'll refer you to these slides. Stochastic optimization method. It talks about these three methods. The first one, which I talked about already, and two improvisations. Actually, they themselves slides adapted from Ryan Dipshirani. So I think there's a legacy of how these slides have been built. So I just refer you to those slides. Let's go back to our main slide. So this as I said, this is the initiation of that entire work thread. So let's understand how it helps in speed up. It turns out that this has an implication on speed up as well. And for strong convexity, that's exactly where we wanted to make that improvement. Now we have something interesting. So remember, for gradient descent for strong convexity, we had this, right? Which we were trying to match up. So it turns out that while you had omega 1 minus mu by L whole raised to t, here your omega 1 minus min of mu by n, comma 18, some 18 factor comes in 18n. So this 1 minus something, the whole raised to t. So you still have that. The implication is basically if your batch size increases, right? And so the asymptotic case will become basically gradient. You can basically verify that. Okay, mu remains a strongly convex case. So this speed up is also observed in practice. So which means that the hybrid stochastic gradient descent indeed is a very effective idea in practice. And with all the other engineering tricks I talked about, in fact, all these I mentioned, right? Stochastic variance reduced gradient, SVRG, and then proximal methods we'll talk about, but we won't talk about SVRG or stochastic dual coordinate descent. I think even Pradeep Ravi Kumar's slides doesn't have many of these. Um, you could pick some of these for your seminar if you want. Okay, I think I've listed them in seminar. These are potential seminar topics. Um, yeah. Any questions on this? Okay, so it's just one illustrative slide to show how the stochastic average gradient has made a big difference. The one in pink here. in compared to say comparison to say the stochastic gradient descent. I didn't talk about LBFGS etc., which are quasi-Newton methods. So basically, where you look at uh, kind of surrogates to your Hessian matrix, which can be used to account for the curvature of the function. Okay. Um, so now we'll study some more variants of SGD which are commonly used in deep learning. So we're going to jump a little bit from the history 2012, 13, not go through that entire trajectory to what gets used nowadays, right? And present a more generic architecture wherein you can basically pick recipes. Um, and we'll worry a little less about the theoretical convergence results, as I said. Many of these analyses are actually for convex case. Okay. So, but the motivation for non-convex is the same as that for convex. So convex, what happens is very interesting. For convex optimization, see a gap, right, and that you try to bridge. But the process by which you're trying to bridge the gap has also benefited the non-convex optimization problem. So I didn't bring this as an important outcome of convex analysis, but let me write this down explicitly. Okay, so note an or hidden advantage. So we saw gaps. In which what cases did we see gaps? Can you recall? Lower bound and upper bound, a lower bound and the actual algorithm we've seen in one case, right? Just after midsems. And that was through existential, right? The lower bounds were attained through existential, existence of certain functions which are hard to crack. Yeah. Smooth and strongly convex lower bound versus gradient descent, right? And that basically brought in accelerated gradient descent. Smooth and convex, not strongly convex. Yeah, right. Correct. Or in the previous case, right? Such as what did we see in the case of stochastic? Correct. In fact, both strongly convex and convex, both there were gaps. I didn't show the case of convex, but strongly convex, we seem to have gotten into some familiar territories. We got a exponentiation with respect to t, which means linear time under certain settings. So strongly convex and SGD versus strongly I would say strongly in bracket. And that led to um, what did that lead to? It led to stochastic average. Okay. So I think I should just move to the next slide. Yeah. We then try to bridge such gaps using improvements. That's what I meant, right? Now, but it's not that these the improved algorithms benefit only the convex case. Okay, but we are going to take a little bit of plunge and may not even state analysis in many cases. Like we've been at least stating analysis, though we stopped proving since a couple of classes. So I mean, we already have enough reason to now look at Nesterov's adapted versions, right, for improvement. Um, and we have seen how we can get the constant additive constant. Like those two we'll try to bring together, but we'll try to bring them all under one umbrella eventually. Um, there's one new dimension we're going to add, which is adaptive methods, and that adaptive especially specifically for learning rates. Okay, so we did try and talk about Armio condition. That's another thing we again maybe I should have mentioned that here. Okay. Um, Also adaptive learning rates motivated by Armio conditions. There are lots of Goldstein, Wolf conditions. Also motivate adaptive methods such as Adam. So you see the list here: Adam, Adagrad, which are algorithms you typically use. Okay, so all of these do owe their genesis to lots of adaptive learning rates in the non in the convex settings. Though I also did point out that there is a connection between the adaptive methods, uh, especially learning rate sensitization methods, and the momentum methods, right? The only thing is momentum is also accounting for direction. So we'll see some of that coming back. Okay. So with that kind of preparation, let's move on. Unless you have a question here. Okay, so I just want to again highlight that theoretical convergence results may no longer apply. Okay, so let's start with SGD and momentum. Simple integration of stochastic of momentum into stochastic gradient descent. So this is SGD. Can you propose how you would incorporate momentum here? What would you do? WT plus 1 is WT, and then what else? Any variant you can suggest. Okay, so you could have velocity, but velocity could be incorporated into the gradient computation or may not be incorporated, right? So how about the following? I'll just say minus alpha t gradient. Now I'll still have this index it, okay, but wt I could have the velocity already integrated through a gamma t. So gamma t I put this because I mean momentum methods we've seen that they do look at adaptive versions of gamma, etc. So there's a gamma t, and you can look at wt minus 1 plus what? So this is the gradient part. Can we also have the explicit velocity? Question is that with the explicit velocity, should we have gamma t or some other parameter? Should we have the same thing, gamma t wt minus 1 in the velocity or something else? You could have same, right? But in a more general setting, you could just say this is a different parameter beta t. I'm doing that because let's say I wanted to recover the heavy ball method. And if I made gamma and beta the same, then how would I recover? In heavy ball method, what happens to gamma t? 0, right? But I don't want the last term to go to 0. So what is your expectation? What would so this is the, let's just move, right? This is the overall update scheme. So let's write down what would happen with heavy ball. So we'll abbreviate heavy ball as HB, and this is also the polyax heavy ball. So as you pointed out, gamma t would be 0, and there would be a scheme for beta t. We can fall back upon the expressions we had earlier. Um, with Nesterov, okay, this is also called accelerated gradient. I think we'll call it accelerated stochastic gradient descent. Yeah, what would happen? Gamma t would be beta t. Okay, now I'll be adding a little bit more complexity. So we are starting just from recapping. But we also look at adaptation beyond just getting the gammas and betas adapted. We'll also try to bring in a little bit more curvature information. That's how things are state of the art. Okay, so let's. So okay, heavy ball momentum, gamma t is 0, and Nesterov accelerated gradient NAG is gamma t is beta t. I think I should just correct this. NAG. That's the notation I used. Okay. So there's an issue that these are not adaptive. Adaptive in terms of the behavior of the gradients. Okay, so when I say adaptive here, I am specifically saying gammas, betas, or whatever adapting to if you remember RBO condition, there was a sufficient decrease condition, right? That we looked at, the fact that I don't want to overshoot my minimum. Okay, so without the right learning rate schedule, otherwise you can have nightmarish time converging at all. So the fix now we'll discuss. This is where we are going to look at slightly non-trivial updates. Is adapt the learning rate based on gradient information until now. Okay, so that means you're looking at GT minus 1 and so on. Okay, so I just draw a quick relationship, with Newton's update. You probably may not get time to do it. If you get great, but there's something called Newton update, which will probably be related. So in a Newton's update, what would you do? You unlike gradient descent, where you say xt plus 1 is xt minus, right, some gamma of the gradient of f at. Okay, I should have used w. I'm sorry. Since you're doing machine learning, I'll just use w here. Okay, so this is what you do, and this is basically a first order approximation, or the first order function approximation being minimized. Okay, you can show that this is equivalent to minimizing a Taylor series approximation with just the and use only the first until the, well, basically second order term, right? But where you use a second order term to be a constant, you're in kind of ignoring the variableness brought about by the second order derivative. So in one sense, it's just the first order derivative used. This is rather minimizer of Taylor series approximation. So limited until the gradient term. Okay, so yeah, let me just sorry. Okay, so this is the this is what we ordinarily use for gradient descent. But now we want to go beyond and say, well, we want to do something with respect to this adaptation that I've talked about here. Let me just use a different color. The fix, this is a fix we are talking about, where we want to make use of the gradients, but um, as I said, this is going to be inspired by the Newton method, which says instead of minimizing the Taylor series approximation and limited until the gradient term, you also look at the second order, limited to until the second order, which is the Hessian term. Okay, and that gives you a slightly different update. You can have a learning rate there also if you want, but it becomes less sensitive to that. And you could look at the Hessian. Okay, so this Hessian. Okay, so this Hessian, when you multiply it with the gradient at the current term, is also kind of accounting for the curvature of the function. Okay, so going back to our example in the past, if you had ellipsoids, these are the canonical example to motivate. This is a canonical example to motivate the Hessian use of Hessian as against the gradient, right? So, what would the gradient descent do? It will basically take steps perpendicular to the level curve at every point. So let me use a different color for these. So your gradient updates would say, okay, I'll go perpendicular here, and then go perpendicular here. So there'll be a lot of wobbling around. Actually, in fact, I've not shown very. So there'll be some. Okay, whereas the Hessian based update, even if I'm beginning somewhere like this, it'll detect that the overall shape is curved towards this guy. So it's going to, in fact, you can even take large steps around this, right? So it'll move very quickly along these in this direction. So it's not just behavior of gradient at the current step, behavior of the GTs. That's why I said, right? The curvature. Hmm. That's exactly the point here. Yeah, but this is just a motivation. We are not going to use Hessian. That's very important. Okay, this is, as I said, this is a motivation or related. So this is somewhat related to Newton's update.
In the previous slide, why was there FP like
Why was there a
FI is not needed? So why there are other functions only?
Fi? No, Fi is the gradient of the loss with respect to I teeth. IT was a so if you see, we had an IT being sampled everywhere, right?
Yeah.
Okay, so this IT, okay, yeah, probably missed that.
Subscript is an I.
Yes, subscript is on I. IT is the same as IT example. Is it clear? Thanks for asking this question. Okay, so with this motivation, let's move on to the adaptive gradient descent framework. Okay, what we'll do is this adaptation we will do through this new magical, somewhat magical matrix called H. Okay, so we'll have an H T or H capital T or small t. So this H small t is basically your think of it as an approximation to the um, a surrogate to the Hessian. Okay, but we may not use the Hessian actually to compute it. We look at the interactions between the GTs. Okay, what's the time? Okay, this is captured interactions between. Okay, so with that background, let's look at this adaptive gradient descent framework of algorithms. So HT is this. By the way, the Hessian is supposed to be a positive semi-different matrix. That's another thing we should note. Okay. So yeah, let me just note that. Should be positive semi-definite. Okay, so we will ensure that throughout. So it's a positive semi-definite matrix, but how do you compute it is what we will discuss now. Um, so simplest definition is a diagonal matrix. As I said, interaction between the GTs. So if GT is gradient of f, uh, you can put an index IT if you want, but I mean I just made it simpler. So then gradient of f at with respect to WT, then you're looking at the outer product. Okay, so this is called outer product. Outer product interactions between the different T's. Okay, so this GT is evolving over time. And you're trying to now capture the revolution over time instead of looking at the second order derivative. Because these are anyway stored, they're available. I mean, at least some of them are. Okay, so this is a diagonal matrix. So this looks like this. This is a diagonal HT is a diagonal matrix where these elements are zeros. The off diagonal elements are zeros, and these elements um, are exactly what we are showing here. Okay, so this entire expression raised to half. Okay, let's understand a little bit more of what these outer product is. So rank one matrix, we have seen this before, right from when we talked about low rank approximations as one motivating machine learning problem. We actually talked about such rank one matrices. So rank one matrix is also called based on outer product. Okay, so yeah, this exactly is outer product. Okay, and I've written more specifically. If you want how exactly the expressions look like, this is how you compute. That's all you need to do. H T inverse jth element, the diagonal element, is just this. Okay, it's very simple.
You integrate in the half there, the power, then you receive the matrix root over in terms of the diagonalization.
Matrix.
Because GG transpose is the outer product, it will be a matrix, right? So you put a raise to half there. So what does that mean?
Basically square root, because all others will be zero. You're only dealing with the diagonal matrix entries. You'll basically take.
So the square root will continue.
Yeah, yeah, thanks. Yeah, that should have been here as well. Yeah, I think this summation raised to half. Yeah, good. So the adagrad is the simplest adaptive algorithm. So now the adaptation is what alpha t you have. You still have alpha t, but you're not over dependent on alpha t now, thanks to your curvature matrix ht or its ht inverse. And this alpha t is also the base learning rate. It's not the only learning rate. I mean, this is just a base. Okay. So we'll now look at how all of this can be put together. We want to now put together the adaptivity with acceleration. Okay. So in the previous case, we just put the adaptivity here. That's all we did. But now you'll have acceleration and all of that. So I'll be presenting a table right below. But before that, let me again get you warmed up. Um, we'll introduce some notation where the dt is a diagonal element of the gt into gt, right? The basically this gt into gt is what the element wise product. Okay, I've written it here. Diagonal of gt into gt. That's how you got the gt square, right? Gi t square. This expression. So gtj square. Sorry.
And this is the outer product.
This is not the outer product. This is element wise product. Yeah, yeah, yeah. GTJ square, right? So what we saw there in the previous slide, this GTJ square. So you could think of, yeah, let's proceed. You could think of actually HT as its diagonal elements will be derived from the DT. So we can actually unify all of these into this single update equation. Um, GT, I'll show you what different versions of GT are for different algorithms. So GT, for example, could be I, the identity matrix. Okay, possibilities. For GT is one is identity matrix. For example, if you're doing non-adaptive, right? If you're doing non-adaptive stochastic gradient descent or momentum, then GT is just I. And we'll see there are some other variants where it could be some function, of say GT minus one and the current DT. Okay, where again I repeat the DT is just GT1 square, GT2 square, and GTJ square, which you saw in the previous slide. All other zero. This is how DT is looking. Okay, so the rest should be straightforward, but this HT will now be derived in terms of the GT. as square root of gt. Now with different choice of gt, you will get different variants. Is that clear? So the table will be listing out what gt variants are. Also, one more point. Um, you'll find this. Let's get the intuition correct. Okay, so this ht inverse ht minus 1 you see there here, right? See, the velocity has to be somewhat pure, right? You don't want the velocity to be too much affected by your curvature learning rate, right? So velocity is just how things have been moving. So this is kind of, I would say, pure velocity term, pure velocity discounting. Okay, I'll just type it easier. I kind of discounting for the Hessian. So therefore, you'll find that I mean it's not really Hessian, but h over time. So this you'll find that there's a ht inverse into ht minus 1. Okay, that's what we mean by discounting the effect of h over time. Okay, as I said, this is a kind of umbrella expression. Oh, ht is accumulated until now. So it will be small, it's the same thing, small t. So this is because there's an accumulation of t equals 1 to capital T. Yeah, but this t is an index in, see, if you want, you can call this t prime, and replace this with t.
Does in the second equation the sum will be not consecutive?
Here it should have been, oh,
Point one.
correct, correct. This should have been, that's all, yeah. Otherwise, others are okay, right? As I said, you have become a little robust to notations here. So, but yeah, this was a genuine mistake. Okay. Um, are we fine otherwise? So now we'll just unfold the table. Let's look at the table. So, as expected, I think I mentioned this already here. The GT, okay, I mentioned the previous slide. Right? GTI, that's this case. If GT is I, you will basically get all the non-adaptive versions. These are all non-adaptive. That's what I expected here. This is a non-adaptive version, which is making sense, right? So there's always going to be in I. HT inverse will be I. HT minus will be I. Everything will be I. So you're just getting back the non-adaptive case. But by now changing the form of GT when it's non-identity, you are basically now recovering three different algorithms: AdaGrad, RMS Prop, and Adam. Okay, so in AdaGrad, you're taking the previous GT minus 1 plus the current DT, which is DT is, as I said, just the diagonal of all the gradient component squares. Um, so think of this GT as the accumulator, squared accumulator. So think of this GT, that may be a good. So think of this GT as a squared. Let me type. Oh, we are already 2 minutes beyond time. Yeah, squared. Okay, therefore we have to do a square root uh, before actually using it, and you're just adding the square of the this dt minus 1. Maybe just copy this for, so the square of dt you're just adding everywhere, so that your current curvature is being accounted for in the squared accumulator. Now the difference is whether you take a a convex combination like this gt minus 1 plus dt, right, or just this basically beta 2 is half in Adagrad case. Whereas in Adam case, you're doing slightly more, right? I mean the you're also looking at the not just beta 2, but there's also something called a beta t. How much to weigh is also you're learning that from history. That's beta t sitting here in the Adam case. Okay. Um, yeah. Uh, so this beta t itself has a row here. So I think this beta t in the case of SGD, HB, and NAG are all constants, either zero or some constant value beta. Adagrad, RMS prop, they are zero, but there's this value of beta t. So this beta t which you saw here, um, I'm just going to highlight it. This beta t, which is consequential only mainly for Adam, is listed here. So it's basically it's looking at the evolution of the beta across time and using that for your update on the GT. Okay, but then gamma is zero in all except the NAG case. So gamma is just very purely for accelerated gradient. I mean, you could have just ignored it other than the fact that it matters for uh, Nesterov accelerated gradient. So this is gamma doesn't matter otherwise. Okay, so the only the I would say the only tricky part here is this beta t. Others are very intuitive. Why the exact application of beta t is of this form? Yeah, probably can read up a little bit more on the Adam paper, but I'll give a little bit more narrative of this in the next class. So just maybe internalize this one slide for the next class. I'll just say homework.
What does it indicate? Is that the value of beta 2 or
This yeah. So this says GT is updated. This is update.
update means that like the value of beta 2 plus 1 will be less?
Uh, Sorry, can you repeat? Beta t will be updated to beta 1 into 1 minus beta t minus 1.
Will this be where is the
This is beta t, which was updated already.
beta t is particular to here?
Wait a second. Oh yeah, that's a good point. Is there a okay? This the denominator beta t, right? Yeah, that's a good point. Um, no, this has to be. Let me just check this. This needs to be verified. Yeah, this beta t is otherwise okay. I think this denominator is a concern. I'll look at it. Yeah, thanks. Okay, we'll conclude here. It's already 5 minutes past. Thanks for your attention.